This week's activity is plastics processing, which you're going to perform on this machine right here, which is a small benchtop injection molding machine. I'm going to go over the parts of the machine as well as some of the tools that we're going to use over the course of today's activity. And then we're going to make some parts. The parts we're going to make today are golf tees. And we're going to create consecutive golf tees, improving them each time until we make the perfect golf tee. And then in this holder right here, we're going to make 10 identical perfect golf tees. That's what we're going to take into the other lab to do impact testing, which is just like what we did last week. We're going to destructively test the golf tees to find a measure of impact strength, and that will help us identify what the plastic is. The plastic is in these little coffee jars here, and this is polymer A. So you would write down which unknown polymer you have if you were in lab. So on my data sheet here, I'll make sure to write at the top that I have polymer A. And this sheet is what I'm going to use to track my variables as we progress through the activity. One of the variables that we're going to be measuring is the temperature of the mold, because that is a specific type of variable that will influence the quality of the parts. So the first step is going to be to identify the parts of this machine right here. And I want to bring the camera in a little bit closer so that I can go over these in greater detail. Now that we're in a little bit closer and can see some more detail here on the benchtop injection molding machine, I'm going to talk a little bit about the features on the machine, its parts, and how those relate to variables that we're going to change. The construction of the machine is different from what you saw in the diagram from our introductory slide set. The introductory slide set had a picture of a reciprocating screw type injection molding machine. That's a machine that has this screw that both turns as well as retracts and advances to inject plastic into the mold. This machine is a little bit more simple, a little bit more rudimentary. It has a heated barrel down here into which we put pellets, and it has a mold right here which is clamped in place, which I took a picture of for our slide set. There is no reciprocating screw. Instead, we rely on this heated barrel to plasticate and melt the pellets, which are up here. And then right here is an air cylinder, and this air cylinder, when we apply air pressure, is going to drop a ram and push the plastic through the heated barrel and into the tool. It's a little bit better suited for a small scale process. So we have the frame of the machine, we have a heated barrel assembly, we have a piston or a push rod that comes from our pneumatic cylinder, we have a hopper full of material, and then we have this control unit up on top. And on the control unit we can change a number of things. First of all, we can change the temperature at which this barrel is set at. So if I set this display to SP, which stands for set point, you can see my target temperature is 250 degrees Fahrenheit. I want you to note this temperature because when you do your research to find out what polymer we have, the melt temperature is going to be a really vital clue. And the melt temperature will be very, very close to the processing temperature because we don't want the plastic to burn or to become so liquidy that it flows out of the mold. We want it just at its melt point. So right now I have this display set at 250 degrees Fahrenheit. And you can see that this actual temperature right here of 248 is very, very close to the set point. So we can control the temperature of our barrel directly. The temperature of the tool down here, while we're on the subject of temperature, is also going to change. Right now, this tool is about 83 degrees. It's been sitting below this heated barrel and it's just above room temperature. That is another type of variable, the temperature of the tool. We're going to keep track of it on our data sheet, but it is a distinctly different type of variable from the barrel temp, which we can set as operators. And I want you to know the difference between those types of variables. The next thing that we can control besides temperature is on this dial here, we can set two different times. We can set how long after we push cycle start does the barrel wait, soaking heat into the pellets before it drops the plunger. And then the second time is how long that plunger stays down. So we call the amount of time that we let the pellets sit in the barrel the melt time, and then we call the amount of time the plunger is actually down the injection time. Now, it's worth noting when you look at this dial that even though it is a 0 to 12 dial, the two hands read differently. The injection time in red reads directly in seconds. So if I set it here to 2, it will leave that plunger down for 2 seconds. By contrast, the green dial, because it's meant to be for longer periods of time, reads in tens of seconds. So if I leave it here on 4, that means that it's going to let the pellets soak up heat for 40 seconds and then drop the plunger for 2. So if I were to set both of them here at 1 and I were to press cycle start, then you could count in your head down to 10, because it's going to wait 10 seconds, and then drop the plunger for 1. There you go. So I have some basic settings eventually that we're going to set this to. 20 seconds of melt time and 2 seconds of injection time, and that is in conjunction with our 250-degree barrel temperature. That's going to be our preliminary settings, and we're going to see what kind of product we get. But before we go on to that, there is one more variable that we can change, and that's up here. I mentioned that the piston that pushes the pellets through the barrel is pneumatic. This cylinder here fills with air and drives a piston down, and we can control that air pressure. So right now the air pressure is set at 70 psi, and we're going to leave that for our initial settings, but that's another variable that we can change as we seek to improve the quality of our part. I'm going to get our sheet and I'm going to write down our preliminary settings. I'm going to fill the hopper here with pellets and then shake this little handle until the barrel fills, and then we'll take a shot. So let me get a few more pellets in the hopper and we'll give this a shot. I've tried to pick a view for the camera that lets you see both the barrel temperature at the top as well as the other settings, but it's just too difficult to really pan out where you can see the air regulator. So what I'm going to do is walk you through each shot, and I'm going to give you a view of what our parameters are. And I already discussed what our first parameters are, and there they are written on our sheet. And then I'll go through a shot for each one as we improve the quality of the part. But right now, let's just see what those initial parameters give us. So I'm going to fill the barrel with pellets and then press cycle start. And here you'll see that the machine is going to wait 20 seconds, allowing heat to build into those pellets before it drops the cylinder. It's going to drop the cylinder for 2 seconds. And what I want to do is just see what is the initial shot that we get. Okay. So after the shot, we can see that there's a little plastic nub that forms. That's from plastic entering the mold. And so what I'm going to do is use a scraper here to scrape that flush, and then a brass pick. We always use a brass pick when dealing with sensitive tooling because we don't want the pick itself to damage any part of the tool. So I'll use that to eject our part. And our part is really not yet a golf tee. It's quite a bit less than a golf tee. It's a little bit more like a nub of a golf tee. And so here I have to make a decision about what is the change that I'm going to make. And in my slide set, I mentioned that scientific method leads us to only change one variable at a time. So here I've filled out on our data sheet, I've filled out description of defects on molded part, incomplete. It's a short shot. So what I think we want to do is start increasing the melt time. And so here I'm going to increase the melt time 1 second at a time and see if we get any real improvement. So I will reload the tool, refill the barrel, and now with my new settings, start the machine. Okay, I'll remove the tool. We have another little nub there. And here I have to make a comparison between this, the most recent golf tee, and the one made before. And clearly we're seeing an improvement. The tee is just a little bit longer. So for the next few videos, I'm going to be increasing some variables. I think that in the order to make this video expediently, the remaining videos are just going to be a brief title card of the parameters and then a short discussion of what the shot looked like. Just so that we can move through this without you actually waiting for the 20 seconds in between each shot. So I'm going to continue to increase the melt time, the injection time by 1 second at a time until I no longer see any improvement. And then I will change another variable. Here is our third shot, which has all of the same starting parameters, except that the injection time is now 3 seconds. And we're definitely still seeing some improvement. Here is the second part that we made, and here is the first part that we made. So I will continue with the same parameters, just increasing the injection time 1 second at a time. Here is shot number 4. Again, this is with a continually increasing amount of injection time. And there's still a pretty modest improvement there. If you look at the previous 3 shots in my hand, but it looks like maybe this is starting to taper off. So I'm going to continue increasing the injection time, but I'm going to start thinking about what is the next variable that I would change to improve this. Okay, time to look at our 5th shot, which is 6 seconds of injection time. And now that I look at this one in comparison to the previous 2, I'm going to make the call that we are seeing diminishing returns in the quality of our part. So I want to find another variable to make changes to. I'm going to cease changing the injection time, and instead I'm going to start increasing the melt time. So the melt temperature, sorry. I want to increase the melt temperature because the higher the melt temperature is, the less viscous the plastic flow is going to be. So I'm going to go to my set point, and I'm going to start raising the set point 10 degrees at a time. Now I've got to wait until the temperature gets up, but as soon as it does, I'll take our next shot. Okay, here is our shot, our 6th shot. So this is with our increase in barrel temperature by 10 degrees. And that's a pretty dramatic improvement. Here is our 7th shot after we've made some corrections to the soak time. And we'll see if we have any higher quality of a tea here. And we do. We were able to minimize quite a bit of the flash that we saw on the last tea. There's still a little bit there, so I want to take one more shot, reducing the time here to just to 1 second of soak time, and we'll see what the shot looks like. A little bit of fine tuning. We're starting to reduce our melt time to try to control our flash. And I think we've done it. There would be, I think, the best golf tee that we've made. So now on these settings, I'm going to make 10 perfect golf tees, and then those tees we will take into the lab and we will test. Now that we've made our 10 perfect golf tees, we want to take a mass for each one. And we're going to do that for 2 reasons. One, for materials like this, which are not transparent, there is the chance that there could be internal voids, defects, gas bubbles, things of that nature that could influence the impact strength. If there's a bubble right where we test it for impact strength, that can cause an outlier in the data. And hopefully, by getting the mass for each one of these, that'll help us track those variables. The other reason is that when we're done, I'm going to show you a measurement that I took of one of the golf tees, and using the mass and the volume, we're going to find the density, and that's going to be one of your clues to find the material that we're talking about here. So now that I have our 10, I'm going to take the mass. This is going to be in ounces. And I want to keep these in order so that I can track any outliers. And it looks like we don't have a single outlier. All of them weigh in at 0.045 ounces. Next step will be to destructively test them. The tests for impact strength are going to be done on this machine, which is a benchtop version of what we used last week. There's a hammer and a specimen holder. And when we release this hammer, the specimen is broken and we get a reading of the impact strength. Obviously this is a much more scaled down version. If you were to be in class and look at the sheet that you would get, you would see that there is a column for mode of failure right here. And I want you to track that, and there's a good reason. Think back to when we broke the metal samples. Some of the samples deformed as they broke and others didn't. Some had a ductile mode of failure and others had a brittle mode of failure. Now, in order to demonstrate that, I'm going to test our samples. I'm going to start here with the first one, and then we're going to talk a little bit about mode of failure. So I'll place the sample here. I'll zero out the machine. And then I'll take my reading. Now, before I record that, what I want to show you is that there's really a huge amount of deformation that took place. The specimen actually necked before it broke. And as a result, we wound up with 11¼ inch-pounds. Now there's going to be some math to be done before we can use that, but I'm going to write that down. Now by contrast, I have here a piece of a golf tee of a different polymer. This one should have a slightly different impact strength. And what I want you to do is observe the break as well as the sound that it makes when it breaks. So first of all, that was a much higher pitch break. And also, when we look at that break, it is much more brittle. You can see that this clear specimen was much more brittle, had a much lower impact strength. In fact, that one registered down here almost at 0, possibly the smallest amount that the impact tester could record. So when we talk about impact strength, regardless of the material, things like ductile breaks, brittle breaks, high and low impact strength, and the ability of the material to deform are all common characteristics. Now I'll go through and I'll test our remaining 9 specimens. In order to wrap up this week's activity, now that we've gathered some data, we've got a little bit of math to do. I want to share with you my data sheet. And on my data sheet we have our masses for our golf tees. I accidentally put the impact strength over here and the mode of failure column, but that's okay. You can still use these numbers to help evaluate the what type of plastic. The first thing you're going to look at is right here in barrel temp, the process temperatures. You're going to be looking for a plastic that has a melt temperature around this range, around 250, especially 260 degrees Fahrenheit. So that'll be one clue. Let's look at the mass that we collected. It was pretty much all uniformly 0.045 ounces. So how can we turn that into a tangible value that you could use to look up online? Well, if you think about our golf tee's shape, it is essentially 2 cones. And we can find the volume of a cone with really just a few measurements, with the height of this section here and the height of this section here, and then 3 diameters. We need each of these diameters, and then there's a formula which is a little lengthy. You can look it up online if you want, but I'll actually walk you through some of the math right here just to try to keep it brief. But our golf tee was pretty simple in size. We had a 0.48 inch diameter here, 0.312 inch diameter here, and a 0.145 inch diameter here. This section was 1.6 inches tall, and this was 0.15. So if you go online and you find a calculator, or if you do the math longhand, what you find is that the volume of this top half right here is about 0.01875 inches cubed, and then the one below it is about 0.068 inches cubed. So when you combine those two, you're going to end up with a volume of 0.08675 inches cubed. And we know that the mass is 0.045 ounces. So that means, if you remember that, mass over volume equals density, then the density should equal one of these numbers over the other. And then the result you'll get there is 0.519 ounces per inch cubed. Now, when you look up these numbers online for different commodity plastics, they may give this to you in pounds per inch cubed. There's 16 ounces in a pound, so you just divide that number by 16, and that'll give you 0.032 pounds per inch cubed. So this is one of your hints right there. The other thing that you're going to look for is the impact strength. And the impact strength that I gave you is in inch pounds. And you need it in foot pounds. So you could take these numbers here, basically multiply them times 12, and you'll get the range of values. So for this sample right here, 10.5, you're looking at something over 120 pound-feet per inch is going to be the units you're looking for. So if you jot down those numbers, use your multipliers here to find your range of values for your impact strength in pound-feet per inch. I just gave you the density up here in inches cubed. You may elect to use a variety of online resources to find out what this plastic is, but my favorite is mattweb.com. So go back to the list that I gave you earlier in the slide set, look at the series of plastics that I gave you, and then try to identify which one we use today. I can guarantee you it's going to be on your evaluation, so make sure you do a good job.